Ready? Okay, quick bit of discovery work. So let's draw a right angle triangle, and I want your right angle triangle to have use a ruler, but I want it to have the arms of the right angle, two sides that make up the right angle, of unit length 1. 1 and 2. Yep, thanks. Like so. And I'm going to give you 1 minute to work out the length of the hypotenuse, and you need to work it out exactly. I'll pause the video so that I'm not overextending the length of the video. I don't want to belabor this too much, so either you've got it or you haven't. So you should have used Pythagoras' theorem, and Pythagoras' theorem says that the hypotenuse squared is equal to the square of the other two sides summed together. So that will give you 2 because, hang on, we'll just check. Finn, what's 1 squared? 1. Good. So c squared is equal to 2, therefore c is equal to the square root of 2. Boom. So that's our triangle there. Now, what kind of triangle have I drawn if I had to categorize the triangle? Isosceles triangle, because it's got 2 equal side lengths. Can you please fill in the 2 missing angles? You just need to use the property that it's an isosceles triangle. I didn't even bother pausing the video for that one because either you've got that or you haven't. And did you know that today is International Radians Day? Yeah, well, it's not, but anyway, I'm going to work in radians today. So that makes that 45 degrees. Okay, both of those are pi on 4, 45 degrees. I'll keep on interchanging this language because you desperately need to make sure that in your head you're translating pi on 4 as a 45 degree angle without even any thought. Just like, you know, when you get really good at a foreign language, when you're good enough, you can basically, when you hear it, you know what it's saying without having to translate it to English. That's what you need to be with angles. So we've got pi on 4 there. Okay, now what I want you to do is I want you to work out what sine of pi on 4 is according to this triangle. So SOHCAHTOA, you're just working out what sine of pi on 4 is using SOHCAHTOA. Not even pausing the video because I'm expecting you'll be able to take one of those pi on 4s and look at it and go, what's opposite, what's hypotenuse, and put those two facts together. Did you get 1 on root 2? Yeah, 1 on root 2. Have a look at your yellow formula sheet, or look at someone else's, you know, don't mind. What does it say? That's 10. Look at the signs, right? I just have a look at someone else's.
Root 2 on 2.
Yeah, it says root 2 on 2, right? Root 2 on 2 and 1 on root 2 are the same value. And if you did grade 9 maths extended, you might understand why, and if you didn't, you're about to find out. It is a common practice when, to rationalise the denominator, which means that as mathematicians, we don't like to see a square root or a cube root or whatever in the denominator part of a fraction. And the simple process is to multiply the top and bottom of the fraction by that irrational bit. Irrational is the root 2. Irrational means it can't be written as a decimal, simply as a decimal. Okay, so if I do that, I get 1 times root 2 on top, which is root 2, and root 2 times root 2 is just 2. Is that okay? It's called rationalising the denominator. Can you please work out what cos pi on 4 is? What's the cos of 45 degrees? Same action, go. It's just root 2 on 2 again, isn't it? Sorry, spoilers. It's root 2 on 2 because of the fact that it is an isosceles triangle. So the adjacent value is the same as the opposite value. So they're both 1 on, and then root 2 for the hypotenuse. Okay, so cos pi on 4 and sin pi on 4. The only thing we're missing is tan pi on 4, so let's quickly do that. Give you 30 seconds to do it. It's pretty complex there. If you need your calculator for this, please feel free to use it. I'd recommend using your GTC for these sorts of complex calculations though. Opposite over adjacent, so it's just 1. Okay. Tan pi on 4. So, because isosceles triangles are a rather neat category of triangles, and because all isosceles triangles are just scaled up versions of this, these 3 values are common values that are used within mathematics and physics and engineering and stuff like that. So we tend to use these exact values wherever we can. The problem with using approximations is that sometimes if you've got an approximation and then you multiply it by another approximation and then add something else in, excuse me, you start to compound all the approximations and then you get something which is quite out. So where we can use exact values, it's useful. And in trigonometry, the exact values are the sine, cosine and tan of pi on 4, 30 degrees and 60 degrees are the other 2. So we work in exact values where we can. Let's do a new construction, so a new triangle. This time I want you to draw an equilateral triangle as best you can. Use a ruler, please, if you don't mind, but you don't have to obviously use a protractor or anything for everything. Just make sure it just looks like one. Bit dodge, that's okay. Now, are you ready for something fancy? I want you to draw in a perpendicular bisector. Yeah. So perpendicular means at right angle to the base. Bisector means it's going to cut it in half. So draw in a perpendicular bisector. I'm going to draw mine in a different colour. Like so. So there's our construction. Once I've drawn my perpendicular bisector in, you can see that my triangle is just not an equilateral triangle but it's meant to be. Okay, the 2 sides that are untouched, I want you to give, because it's an arbitrary equilateral triangle, right? Let's make each of the lengths here 2 units long. So this is 2, this is 2, and then what's the bottom going to be? 1 and 1. 1 and 1. Okay, everyone following me so far? Okay, so we've got a really common triangle, an equilateral triangle, which we've split into 2 right angle triangles. It's an equilateral triangle, so what are each of these angles, ignore the blue line, the blue dotted line, what are each of these angles worth if it's an equilateral triangle? 60 degrees. 3 times 60 is 180. Okay, equilateral triangle, equiangles. So 360-degree angles. So let's put in the base angle there. Let's just use one triangle. This is going to be 60 degrees. And then what's the angle at the top going to be if I have split that angle in half? Oh man. I said it was International Radian Day. What should I put there instead of 60? Not quite. Pi on 3. Yeah. And half of pi on 3 will be 30 degrees. So it's pi on 6. That's what he said. What did I say? I thought I said what's pi on 6? I said what's 60 degrees? Yeah, but I was 1 step ahead. That could be the title of your autobiography. 1 step ahead. I was trying to do that. Good the video's captured that better, isn't it? Okay, pi on 3 and pi on 6. I don't know about you, but I kind of remember radians, for these are common radian measurements. So I kind of remember pi on 4 is 45 degrees, they both have a 4 in it. And then 60 and 30 just swap over, so pi on 6 is 30, and as Finn knows, pi on 3 is 60 degrees. So the 6 and the 3 kind of switches over. I don't think it's international radio, I think it's just international pick on Finn Day, sorry. Okay, so can you please work out sine, cosine and tan? Let's just stick with pi on 3 first. So remember that's 60 degrees. So let's work out what sine of pi on 6 is, cosine of pi on 6, and tan of pi on 6. And hot tip, what will we need for the first, well, all three of them actually. What will we need for sine and tan that's missing from this diagram? Oh man. We need to work out what h is, right? The height of that triangle. So work out what h is, and then work out sine, cosine and tan. I'll pause the video because there's a little bit of calculations that need to be done there. No, it's not root 5. Okay, really quickly. Sine of pi on 6 is opposite over hypotenuse. So that's x over x over 2. We don't know what x is, so we're going to have to work it out. I'll just do it over here. We've got x squared is going to be the hypotenuse minus the other side length, which is 1 because we halved it. So that's going to be equal to 3. So x is equal to the square root of 3. So sine of pi on 6 is root 3 on 2. And that makes sense enough, I think. And note that the denominator is already rational, which means that there's no square roots in it at all. So we don't need to rationalise the denominator. Cos of pi on 6 is adjacent over hypotenuse, so it's just 1/2. And tan of pi on 6, yep.
The first one, when you use the 1, not the 2. I mean, not the x. Yeah.
What have I done wrong?
Use the adjacent instead of opposite.
Yeah.
Sine is, I'm working from the top, sorry, I think I was working from the bottom. Gee whiz, I'm an idiot. Okay, thank you. But look at this though. When I do this, do you see that sort of like all I'm doing is I'm swapping over the tops of both of these? So my point being is that there's definitely some sort of reciprocal relationship between sine and cosine, and you can sort of see it really coming to play here, that you've got the 30 degrees here and you've got the 60 degrees here, and they kind of complement each other in their sine and cosine values. So that might give you a hot tip for where we're going next. So thank you, Hunter, for that. So x on 2 equals root 3 on 2 is the right answer for cos of pi on 6, cos of 30 degrees. And tan of pi on 6 will be opposite over adjacent, so that'll be 1 over root 3, opposite over adjacent. And then if I rationalise that, multiply it by root 3 over root 3, I get root 3 over 3 as being our rational thing. I like 1 on root 3 better, but anyway. Root 3 on 3 is the more accepted definition these days. Can you do the same thing for pi on 3, please? I'm not going to give you as long because you might be able to work it out a little bit faster if you think about it. Okay, so it shouldn't take you too long to have figured that out, because these two angles are basically, they're complementary angles, so they both add up to 90 degrees, and because they're opposite angles in that right angle triangle, effectively what's happening is the opposite and the adjacent is swapping places. The hypotenuse stays as it is, which means that the sine of pi on 3, I can just go up to the cos of pi on 6, see it's root 3 on 2, so that's what the sine of pi on 3 as well is. Because sine's opposite is cosine's adjacent in complementary angles. Similarly, cos pi on 3 must be a half, and tan pi on 3 is equal to the opposite of 1 on root 3. So it's root 3 on 1, or just root 3. Okay, because the opposite and adjacent flip over. And there you go, there's the exact values. Now, I won't get you to write up the exact value table, but just note in your information sheet, you're given that table of values. Even though that took us about 15 minutes to figure out, or 20 minutes, say, to figure out, I think it's worth doing. I think it's worth you actually physically working out those relationships yourself to see where they come from. I think it helps you remember a little bit better, or at least make sense of what you're seeing there. So please remember all of these numbers: root 3 on 2, root 3 on 3. All of these are the outputs to the sine, cosine, and tan functions. They're the outputs. They are the ratio of two sides in a right-angled triangle, and then we extend that definition past 90 degrees. Okay, they're the outputs. Don't get them confused, please, with the inputs, which is the angle. Root 3 on 2 in this context is not an angle, it's a ratio of two sides. Okay, I'm just going to stop the video here, and we're going to move on to the next thing.